Our next presenter is Fawaz Ghali, principal developer and advocate at Hazelcast. Fawaz has over 20 years of experience in software development, machine learning, and real-time intelligent applications. Today, he's going to present real-time stream processing without migraines, which will focus on how real-time compute APIs help leverage the processing capabilities of a distributed cluster, so you aren't leaving large potential performance gains on the table. Fawaz, thank you for joining us today.
Yeah, thanks, Brian. Thanks, everyone, for attending this short talk. For this specific topic, I will discuss is kind of like a description of real-time stream processing, how it works, and essentially I want to make it as simple as possible. So the fact is, I don't know everyone's background, so I will make sure to basically get everyone up to speed with this concept and how you can basically approach it. So I currently work for a company called Hazelcast. So Hazelcast is in real-time stream processing platform. And essentially, the solution I'll provide today will give you some insights how you can achieve it in your domain. So a little bit background about myself. So I'm currently based in Liverpool in the UK, and I wanted just to highlight these two images. Usually, I ask audience if they recognize these photos, but I realized that it might be not easy to do it here over Zoom. So it's like over the left side, these are the beaters, which are obviously from Liverpool. And on the right side here is the Liverpool Football Club. So now you might be wondering why I have these two photos on this presentation. And simply because real-time stream processing is not only domain specific, so it could be in any domain. So it doesn't have to be specific, for example, for finance or for AI or machine learning or even for sports. It could be any domain. Even if you're not using it in your work, probably the fact is you're using some kind of maybe some kind of social platform such as LinkedIn or Twitter, that it is factored in. So just to give you an idea what we're talking about here today. So for some, if I ask you now what real time means to you, you probably get different answers depending on how you understand real time. So it could be maybe a couple of minutes for some, others might have like a couple of days or a couple of hours, but we're talking about sub-milliseconds. So for example, it takes about 1/3 of a second for an eye to blink. So that's pretty fast. And for example, like clap of hands takes 1/1000 of seconds. So these type of events are hard for human to track, obviously. And if you want to write an application to actually go through processing these type of events, it becomes really hard, especially when it comes to scaling these applications. So these applications, as I mentioned, are everywhere. So it could be related to finance or banks, or could be related to IoT devices, smart devices, could be related to hospital or medical use, or even sports or machine learning. So today we'll be focusing on one specific demo, but I will make sure, to explain how you can use this same concept for any domain. So everyone looks at real-time data as a key element when it comes to processing data. And I wanted to basically clarify that real-time stream processing is not only about real-time data, right? Because we need to understand the context. So without understanding the context, it becomes really hard to make sense out of the data coming in this moment. So the secret sauce basically for real-time stream processing is combination between new data, which is data coming in this specific moment, and the historical data, which provides some kind of context for what's going on with the data. So you might be wondering how many is too many. So I had my PhD back in 2010, and I worked as a postdoc for University of Liverpool for over 8 years, and we struggled with handling large data sets simply because sometimes you run out of memory or run out of CPUs or out of computing power. So you want to provide some kind of scaling mechanism where you are able to scale up or down. And the idea of having like, for example, 100 terabyte to process is really bottleneck, especially when it comes to real-time data. So we're talking about over 1 billion of transactions per second, and you need basically to lower latency, because the more throughput you have within the system or the application you handle, the lower latency should be. I will provide some best practices towards the end of this presentation. So you might be wondering now, so why do I need this? What is important? So why I just can't handle it in the similar or traditional way of handling data? Simply because manual analysis, if you want to write an application to handle this type of large data sets, it becomes really painful. So applications struggle usually. I'm pretty sure if you, for example, go to do some kind of shoppings on normal day, it might be like normal behavior. But for example, if you try to repeat the same process again, or for example, on Black Friday, you might struggle with accessing specific websites simply because websites, generally speaking, when they have large load, becomes really non-responsive. And this is exactly what we're talking about here today. So scaling is a bottleneck, and we want to provide some kind of solution for this problem. So first, we need to provide some kind of alerts. So we need to understand what's going on with the data, and also provide some kind of trends. So are we actually providing some kind of context for the data? So are we creating trends over the data? So this is what we'll be talking today about. Obviously, the challenge is to combine between fast data and slow data, because these two types of data come at different speed, and we want to make sure we process the data, or two types of data, at the same speed. So obviously, one way to do it is to split your application or provide some kind of microservices structure. So for those who don't know microservices, it's kind of like splitting your application into small pieces where you're able to basically split it or arrange it on different nodes or different clusters and provide some kind of scaling mechanism for each of these microservices. So once you split the application, it becomes very easy to manage. It becomes easy to handle these small components and provide or use the same component multiple times. And this is key, right? You want to minimize input output as much as possible, because like this will add latency to your application. So by splitting the application into small pieces, or microservice-based application becomes easy to handle. So for example, in this diagram here, you can see we have 3 microservices, and these microservices deal with Apache Kafka. So those who don't know, Apache Kafka is kind of like a platform or open source project which can handle data in real time. You have multiple topics for different types of data, and you allow basically to have some kind of interaction between Apache Kafka and your microservices. Now, obviously this is good because this will allow you to handle data in real time, but we're still struggling to handle data stored on your physical hard drive or in your database. So one solution for handling slow data is to load it into memory. Now, obviously, there are so many tools to handle this, and if I split it into multiple sections with X and Y axis, you can see on the left side, we have either the platform is open source or managed service or in between. And we also have different real-time data landscape in terms of the type of process you want to apply on your data. So it could be, for example, you want to capture it, or you want to transfer it or transport your data, or maybe you want to do some kind of operational transform, or basically if you're doing some kind of AI, and also some kind of analytics on top of it. So we can split the overall for these platforms into 12 sections. So obviously it depends. For example, if you're looking for transport and open source, you're probably looking for a Kafka or Apache Pulsar or Gazette as platform to provide this solution. But I tend to find this diagram is kind of like overkilling, because it doesn't tell you exactly what you need in terms of stream processing or fast data access. So one way to provide a solution is to convert this diagram into two separate sections. So one section is for stream processing engines. So that's on the left side of the screen. So you see, for example, Apache, Kafka Stream, Flink, and so on. So these tools are pretty good in handling data in real time. And on the far right side, we have the fast data storage. So these type of tools provide you with platform to essentially provide a caching solution to your data. So what you want to is kind of like combination between the two, and that's where Hazelcast comes into place. So Hazelcast as a platform is open source platform. It's built on the JVM or Java Virtual Machine. What it allows you to connect multiple sources, because when you deal with the real time, you want to combine multiple sources. For example, the transactional history, for example, or IoT data, or for example, message queue data. And once you have the source, you feed it into the platform. Platform has two main components. So the first one is the streaming compute, which is the stream processing engine. So this will allow you to handle data in real time. And we also have the fast data management. So this is kind of a caching solution where it provides, or it can actually load your data from hard disk or from database into memory. So once we load it into memory, it allows you to access your data in much faster way compared to having it access every time you want from hard disk and so on. Obviously, the platform itself allows you to kind of have multiple clients, so you can connect it through Java, C#, C++, JavaScript, and so on. But if you're not a programmer, or if you're coming from data science background, you might be considering using SQL. So this is similar to SQL. So you can simply write, as I will show you today, way of handling real-time data using just SQL comments. Obviously, when you handle data, you can do some kind of transformation within this platform. You do combine or even stream processing, or you can also have the option to do machine learning on top of the data to provide analytics in real time. Now, the good thing about this platform is not only the scaling mechanism, but also the partition aware. So imagine you have 3 different data sets for different type of data, obviously. So for example, I have a like financial data, for example, stored in a data center in the UK, for example, and I have weather forecast data stored somewhere in the US, for example, and I want to create an algorithm for fraud detection. So usually most applications find it really hard when it comes to do partitioning, because the scaling mechanism, for some, it might be related to data processing, for others might be related to your data. And the solution for both of these comes into place when you actually combine between data. And the compute is partition aware, means you store the data relevant to your process as close as possible. So for example, if you have a process to access weather forecast data, this will be stored in the US data center, obviously to allow faster access to your data. And if you have, for example, a process to handle financial data, it could be stored in the UK data center, and so on. Obviously, this is auto-scaling mechanism, so you don't need, for example, to do it manually. So that's the idea of using real-time stream processing, is the ability to auto-scale, which means you should scale up if you have more data and scale down. So for example, you don't need to select 10 node cluster, for example, and use only one node. And at the same time, you don't want to have a bottleneck, for example, to handle, I don't know, 20 node cluster when you only have 10 nodes. So that's the idea of auto-scaling. Now we have done this study, and we published this use case where we managed to run 1 billion transactions per second with 99 percentile and just 30 milliseconds latency. This was only about 45 nodes. And the good thing about it is the linear scaling. So essentially what we wanted is to add more nodes as we go along. So this is the number we're talking about, to handle like 1 billion transactions. Now, obviously, companies such as, like, I don't know, Uber or Netflix and so on, they handle 10 times this number. So it just to give you an idea, these numbers are really large, and the key element here is to have latency as low as possible. So we compared between different platforms here. So as you see from this diagram here, so the lower is better. So we compared with Apache Flink and Apache Spark, and this is where Hazelcast comes into place in terms of simple application for word counting, and it comes around like probably around 100 or less for in terms of obviously transaction latency in milliseconds. Now I want to show you a demo, and this demo essentially can help you. You don't need to work in real-time scene processing, but it definitely can help you in terms of understanding what's going on within your application. So in here, we have a application that I wrote. I wanted basically to, I don't know, analyze my logs in real time. So if you have application and this application generates thousands of log messages and you want to basically understand what's going on in your logs, so this solution is probably what you need. Sorry. So in this case, what we use is something called Hazelcast Viridian. So it's essentially everything we discussed today, but it is stored on the cloud. Now you might be asking, why do I need to send my logs to the cloud? Simply because if you work with large scale application, you probably have multiple machines, and you don't want to store the application on specific machine. You want to store it somewhere centralized, and the cloud provide this solution for us. So which means you can upload logs from multiple machines into one space, and this is where you can store your process. So in this case, we use the Hazelcast Viridian for it, and the application simply has a IMAP structure, which is like key value pairs. So in here, you can see I have just created a log message, obviously based on elements related to the IP address, for example, and timestamp to create a key. And the value is just simple string message, and of course, the level for this message. This is the map. So you create SQL based on it. So you just need to, if you don't want to use Java or any programming language, you can load it into SQL. So this is if you don't know or you don't want to learn Java or any programming, you can do SQL on top of it. And obviously the client itself will allow you to create the logger. So in here, we have this just logger, which is an extension of Logger Factory. So simple Java, but again, you don't need to create it from scratch. It will be provided to you. And this is the SQL. So if you know SQL, you can see in this image here, I'm just querying my data, and the key is IP address and timestamp, and the message is basically client and level and score. So the score itself is not important, because think about it is if you have 5-level score, you can do classification, for example, on if you want to apply machine learning. But if you have a scale from 1 to 100, it becomes really harder to actually provide the trends. And we wanted to basically just to challenge the application. So in order to proceed, we provide trends for the data. So on the left side, you see the IP address and timestamp. We load it and create trend map within Hazelcast in memory. And we use machine learning using linear regression to predict if the next message should be alerted or not. So the 1 or 0 provide us with a alert message if you want to do alert or not based on previous transactions. So the actual architecture, you see, you read your logs from sources, obviously multiple machines. You attach timestamp and you calculate a trend. You store it into trend map, and once you have it in map, you can do prediction. This is simply a linear regression. It could be any machine learning algorithm, and then you simply output it to SQL browser or web service, or even you can send it to Hazelcast. So this is the actual algorithm here. It's normal algorithm, so nothing fancy about it. We create trend, and from this trend, we create prediction. If the value is greater than 100, we send the alert. Otherwise, we don't send it. Now, once we acquire the data here, you can see this data basically has some kind of alerts, obviously based on specific transactions. So 0 means don't send alert, 1 send an alert. And you have 3 options to proceed from here. So first is to create SQL job. So which means basically you create a job or a process based on the logs messages, and then you load it into second map. Or you can create a pipeline to read from the source and process it. The first 2 options are batch, so these are not real time. Sorry, and the third option is basically the real-time option, where we have something called map journal, which allows you to process the data in real time. And this will provide, of course, depending on what you want. So for example, in this, you can do some kind of filtering for specific values. Now, just to give you best practices, if you want to apply this type of analysis is, first of all, if you want to ingest data, ingest it in real time. You don't need to store it into database and then process it. You want to make sure to process it even before you store it on physical hard drive. If you're not developer, you can use SQL, and you want you want input output, because you want basically to lower latency. Obviously, if you read real-time data, you want just to read it once, which means you should have multiple microservices to process it. You don't need to keep reading the real the downtime. And of course, you need to avoid enemies. So enemies mean network hooks. For example, you store data as close as possible to your process, and avoid, for example, the input output. Also, context switch it between multiple threads within your nodes and your clusters. So to summarize this process here, so first of all, if you want to handle large data, you want to store it on the cloud. It doesn't have to be Hazelcast, it could be any platform, but this will allow you to have centralized place where you can have a fast access to the data. And it depends on which format you want. Usually it's either JSON or a string. A string is faster. And you want to have some kind of map structure where you can have random access and rebalancing between multiple nodes. And also you want to, because it's map, which means it has fixed size, so you want to provide some kind of eviction policy to remove data from your map. And obviously you want to consider security. So because some messages might be secure, so you want to provide some kind of secure solution based on this. Just before I finish here, so if you're interested in this topic, for example, if you would like to know more, we're running a real-time scene processing and conference, and it's just community event where, you know, community and its experience for real-time scene processing will join a roundtable, and will provide also training. So feel free to scan this code if you're interested. And with that being said, thanks very much. And this presentation was useful, and I'm open for questions. Thank you.
Thank you, Fawaz. Appreciate the presentation. Just as a reminder, if anyone has any questions, they can ask it either through the chat window or through the Q&A, all available on the toolbar at the bottom of your screen. Let's give it a couple seconds here, Fawaz, see if a question comes in. What were the dates again? If you could go back to your slide on your webinar that's coming up. Is it a webinar or is it an in-person event?
So this is hybrid. So the in-person, it will be in London, but obviously you can join anywhere from the world. So you can join virtually as well. So we'll provide a training workshop. So training workshop essentially is just to go through how you can get going with the real-time scene processing, and this will give you all the tools you need, all open source, so you don't need to buy or anything like this. You simply just plug it into your platform, whether you're using Windows or Mac, and you should be able to exactly replicate the work. And then we will have a roundtable discussion where we share real-time use cases. So for example, from financial institutions, or for example, from fintechs, or even from Web 2.0, where you have large data amounts, and most companies usually have some kind of solution to provide real-time stream processing. So I didn't mention these examples, but obviously, for example, if you try to log into Twitter from your mobile and from your laptop at the same time, you probably get different feed. And this is simply because the algorithm on Twitter or Facebook or LinkedIn will sense what hardware you're using and how much bandwidth you have. And they want basically to provide different feed based on different infrastructure or different setup for the same user. So they obviously handle 10 times more the numbers I mentioned today. And yeah, to get started with this, you need just to understand the concept. So this is not like batch data, you store it on hard drive and you process it. It's kind of like you want to process it even before you store it, and then provide some kind of analytics based on it. And then if you want, you can have option to store it and so on.
Perfect. Thank you for the additional information. I currently don't have any questions in the queue, but if you want to hang on for another 10 minutes and answer them, that would be fantastic.
Yeah.
Thank you very much for the presentation. Fawaz Ghali from Hazelcast, everyone.
Thank you.
Our next presenter